All right, hello, CNB 1311 once again. This will be video 3. Structural patterns. Now, what does this mean? All this means is that the shape of your building. Normally, we start out laying stuff on a grid, where the horizontal lines on a grid are the beams, and the intersections of those grids are the columns. So, as you can see here, this is a line. There's a line in the intersection then is a column that goes down to the foundation. That's simple. Now we just have us a little box, a little square box, like a gazillion of the residential houses floating around. All right. The arrangement of principal vertical supports not only regulates the selection of spanning systems, it also establishes the possibilities for ordering spaces and functions in a building. Now, what they're trying to get across in all of this stuff that you will be reading, okay, for this, is that you have the freedom to move this. You have the freedom to make this an offset grid. But what's the purpose of the building? If it's a residence, then you need to design the floor plan. And then the floor plan will determine where the walls need to be and what walls are load bearing and what walls are not load bearing. They're just partition walls. If it's a commercial space, what are you going to be doing in this space? Is this a bunch of machinery? Well, if this is a big CNC machine and this is a little machine shop, well, we don't want a freaking column right there. Okay. So again, what's the intent and purpose of the interior space? So balance has to take place. A lot of times, architects will start off with doing a floor plan. What are we going to do with this? What do we want the floor plan to look like? Where the restrooms need to go? Where do we want the people to flow through? If they're desk, where are the desk? Again, if it's an industrial space, if that's a CNC milling machine, where are the lathes going to go? Where's the EDM machine going to go? And that'll dictate what kind of structural system. You don't want a bunch of columns in here if all of this is workspace for manufacturing. What if it's a big auditorium for a concert? Well, you got your stage, and then you got all this seating down here. Well, people don't want to pay for a ticket, and big old columns blocking them from seeing the stage. So again, if you start off with a basic grid and start filling in that grid, and something needs to be here, let's say something needs to be in this area, well, that can't be a column, right? So that means this span has to be bigger. But if it's a multi-story, well, here's a Lego set. First floor offset. There's a second floor. There's a third floor, and you got this wing over here. And then what is that? 1, 2, 3. This is fourth floor, and then we have a fifth floor copia. And maybe this is where the draw works for the elevator, and the mechanical stuff is up on top. Who knows? That's what this whole page is trying to get across to you. There's multiple levels of design. Multiple levels of design. It talks about when two structural patterns cannot be conveniently aligned. Two parallel grids that are offset. A portion of the grid can be dislocated. We just said that. Rotated, offsetted. Maybe it's an irregular grid. This is what you have to do in your first phases. All right, let's move to lateral stability. Lateral stability. Again, we talked about wind loads, remember? We talked about wind loads on a building. You know, the wind's pushing on it, makes it want to fall over. Earthquake loads makes it want to fall over. All right. We talked about if this was pinned, it would just fall over like a Lego box. If we put gussets in here and made this a rigid frame, then it's more of a rigid deal. Now, you can use your floor systems. We call these a diaphragm system. Okay. And they can be cast in place concrete. They can be precast panels that are welded to the beams and columns. There'll be weld plates up in here to make it a rigid structure. It's a horizontal diaphragm. Your load-bearing walls, they carry load. This represents a resistant load from this pushing that way, etc. And the soil goes up, that goes down. Things in what? What's that word? Equilibrium, right? So a rigid floor structure acting as a flat, deep beam transfer lateral loads to vertical shear walls. Braced frames or rigid frames. Any of you have ever done any traditional stick framing, like for a residential house? The frame, even though you get it all up, you can still make it creak and rock a little bit when you're pushing on it. But when you start putting that plywood siding on the outside of it and stitching that plywood siding to the frame, here's the frame. All this is nailed together. This is on the bottom plate. But when we start putting those 4 by 8 foot sheets of plywood on here, and nailing that plywood to the framing, what happens? It becomes very stiff. The wall becomes stiff because these plywood sheets that are nailed to the studs become a diaphragm. They become a shear wall. This just became that, or this just became this, except this is vertical and that's horizontal. This is nothing more than a shear wall that's a floor or a roof. Okay? And it transfers this diaphragm floor structure or roof structure, transfer these loads to the structural system, be it a rigid frame, be it a pin frame or braced frame. Don't you ever do a pin frame. They all have to be braced. We'll talk about that in a minute. Or a shear wall. Best thing is to do a rigid frame. Safest thing. All right, so bracing. We got all kinds of bracing. We have knee bracing. And what do we mean by that? Well, here's the knee. Here's the knee, bent knee, right? That's a knee bracing. All right. Force on the frame goes this way. The knee brace does what? What does the knee brace do? It stiffens it, right? Oh, excuse me, my sinuses are kicking in. It stiffens it. So if it's pushing this way, the frame's going to resist this way. The knee brace is resisting this way. It's in tension because it's trying to pull it apart. This knee brace over here is now in compression. It's pushing down on the column, and the upper diaphragm deck, or the upper beam of the frame. Let's assume this is it here we're talking about. We'd put the knee in here. Okay? Because this is a rigid frame. This has a built-in knee. It's a part of the structure. Usually they would come up and come over with the gusset plate, and then you have a big giant gusset plate where the top of the frame goes. That's one way of doing it. And this is a giant super bolted connection. It's not pinned. It makes a moment connection because that's how it's designed. And it's got moment gusses in here. Or it could be all welded. It could be welded in the field, or if it's small enough to be trucked, it could be welded at the shop and then trucked out and erected. Okay, K-brace. K-brace, why is it called a K-brace? Because it looks like a K. And it works in the same manner. All right, there you go. All right. Wind's going to push on that. One of these is in compression. One of these is in tension with this particular loading. Column has to resist it this way, and the upper beam or the roof deck, the rigid diaphragm, resisting in that direction. Again, we want equilibrium, right? Newton's third law, opposite and equal reactions. Okay, now what happens with the K-brace? Well, we've just lost this bay. With a knee brace, we can still come in here and put a header in, depending on how high this is, with the wall framing, if we were going to frame this wall out. Okay, and we could put a window in here, right? Okay, we could put a window. There's a window opening. All right, but if you're going to have an open frame, then K-bracing gives you an open bay. I mean, knee bracing, in this case, knee bracing gives you an open bay. K-bracing is going to eliminate a bay. So this bay is pretty much useless unless you put a little tiny window in there after you do your wall covering, and then this is open. Okay, that's a K-brace. Now, cross bracing. Sometimes you have to cross brace, and cross bracing is going to eliminate the use of that end bay. Now, if you don't care, let's just say the overhead door was on this end, and for some reason you just wanted the smorgasbord of framing and had to do a K-brace back here, then you put your exterior siding on that, and that's fine. And this works really well as long as your wind is coming in this direction, and that can serve as your shear wall. But then again, your K-bracing will work, and if you want this to be a shear wall, since you can't drive a tractor through it or a truck, you could put a hard panel in here, and it would carry some shear load, just like that wall there. All right, so that's your cross bracing. Makes a giant cross. And there's pluses and minuses to all of this. You'll have to get with your design, what the intent of your building is, and your structural engineer, and talk about that. All right. Any of these systems may be used singular or in combination. You could stack these for a mile long if you had the money. All right. You could take these frames and stack them a mile long if you had the money. You'd need shear walls intermittently through there, but you could certainly do that. A lot of industrial buildings are done that way. Those old Cameron buildings off of 290 are like that. All right, any of these systems can be used singular or in combination to stabilize a structure. The three vertical systems, a rigid frame tends to be the least effective. However, rigid frames can be useful when employing braced frames or shear walls would form undesired barriers between adjacent spaces. Now, I disagree. Rigid frames can be useful when employing braced frames or shear walls. I misread that. I don't disagree. I'm a big proponent for rigid frames. Oh my God, I misread that. Okay. But let's assume that this was a 300-foot long building, and it was going to be a rigid frame span all the way down. You're going to need some kind of shear wall through here, right? If not, this is just going to be a tinker toy set that would fall over like dominoes. So you'll need shear walls. Or you're going to need bracing in between the two. Let's say this was a rigid frame that's going back this way. Oh my God, that's ugly. That's a rigid frame going that way. And this is a rigid frame going this way. And it comes down in the back like that. All right. Well, this would be this bay right here, right? So that K-bracing would come down to the next rigid frame. Maybe that should have been the better way to draw it. Okay. Fire me. And there's your K-bracing in between those two. And you'll see a lot of this K-bracing like that will be cables, heavy rods with turnbuckles once they get the framing up. And then you let your roof system take care of the shear. And then perhaps if it's super long, depending on your wind loading, you may need a concrete wall, solid shear wall like that periodically through the span. Your imagination and creativity is endless with this stuff. Lateral forces tend to be more critical in the short direction of rectangular buildings, which makes sense. And more efficient shear walls or brace frames are typically used in this direction in the long direction. Any of the lateral force resisting elements may be used. Bents, these are called bents, are braced or rigid frames designed to carry vertical and lateral loads transverse to the length of the frame structure. In other words, this is a rigid frame with a rigid beam connection across here. Now this makes more sense, right? The span is less in this direction than in the longitudinal direction of the building. So yes, this is going to be more rigid. Basically, you got two rigid frames welded together. So this is going to be extremely strong in this direction. And you'll need some kind of shear force resistance in this direction. Maybe your calculations, your K-bracing will take it 1, 2 bays, and maybe this bay needs to have a traditional shear wall. Maybe, who knows? Or some more substantial bracing. But you and your engineer will figure that out. Now, if you're doing a prefab metal building from a company that has designed all of this, their structural engineers already have this computer modeled and will be able to guide you on what you need to do. All right, so here's a term, bents. They're basically two rigid frames, and I think you can see where two rigid frames are a bent. We ought to fire the concrete people. That's not very level, is it? Okay, this is a rigid. That's not pinned. That's rigid. So let's get rid of the pin connection. Uh-oh. Too much eraser. We'll come up. We do a bent. That's rigid. That's rigid. That's rigid. And that's rigid. So what have we done? Well, assuming we don't need this height for the full use of the building, then we have two rigid frames, right? You basically have a two-story rigid frame. So this reduced the length of that column. And if you'll remember the section on columns, what happens if you reduce the length? The column of a given size can carry more load, right? And so that's one column span. All right. So this can carry more lateral load that way, and it can carry more load this way. So what else could be done if this was a super duper wide space? Well, you already know. That's right. You got it right. You in the first row. We could come in here in that bent and turn that into a truss. Now what do we got? Super duper strong in this direction, but not so strong in that direction, in and out, down the long axis of this thing. Not so strong in that direction, right? So we still need some kind of bracing and eventually some kind of shear resistance, whether it's the diaphragm via the walls or the roof. They could be a diaphragm. So there's all kinds of things. All you got to do is just be creative and be willing to get out of the box. All right, let's move on to lateral stability, which is what we're talking about basically. We are still talking about lateral stability. My goodness, that's why I don't do cooking shows. What we're doing up here, what he's doing up here, is he's showing you ways in which lateral stability can be gained. And again, this is going to be determined by your structural engineer. Now, let's assume that We don't want the building, if this is a tall building like this down here, we don't want it to twist. Just say the wind's blowing from this direction, okay? And it's a gusty wind. Now we know that the building's going to want to bend that direction. It's also going to want to twist a real bit. Torsional stresses around the center if the wind loading is of a certain direction. Let's say the wind's coming from this direction, off that corner. It's going to produce stresses going in this direction, and it'll produce stress going in that direction. And what's that resultant thing? Come in that direction. So that resultant is going to want to put a little twist to that building. So how do you reduce that twist? You reduce it with shear walls. Now, this particular is showing you discontinuous shear walls. All this would be like a concrete wall with holes punched in it, or cast in it, actually. Maybe it's tilt wall, or maybe it's diaphragms that they attach structurally and rigidly to the frame and produce shear resistance and torsional resistance, okay? So, and this talks about corners, okay, configuration of a structure having projections beyond the corner significantly greater than the plane dimension in given direction. A reentrant corner tends to produce differential motions between portions of the structure. And again, this is structural engineering. Solutions include providing a seismic joint to separate these two so they don't bust apart. There's all kinds of stuff on this, and we're not going to get too deep into the weeds on this. I just want you to understand the concept. This would be a seismic joint, how to isolate the two buildings so they can both move in whatever direction separately and reach different frequencies. He's given you a description of a discontinuous diaphragm. Having a large cutout or open area or stiffness significantly less than the story above or below. You don't see too much of this being used. He's going back to the center of resistance or a centroid. This would be like for a roof diaphragm. Torsional irregularity refers to the asymmetrical layout or mass. Let's say this is an open covering, okay, with a column over here. All right, let's just say there was just columns here. This is going to be less stiff than this. All right. To avoid destructive torsional effects, that's the twisting of your building, and also it helps with your longitudinal shear forces. It should be arranged and braced symmetrically with centers of mass and resistance as coincident as possible. The asymmetrical layout of irregular structures generally requires dynamic analysis. This is high-level structural engineering in order to determine the torsional effects of lateral forces. For mid-rise and low-rise structures, this is not a big deal. High-rise, it is a very big deal. The taller you go with respect to the footprint means more flexible all of this is. Okay? Now, here's certain ideas of what you can do. What is this? That's a shear wall. And torsion is shear, and shear is torsion. Torsion is shear in a rotational manner. Shear is generally a force like a pair of scissors. Scissors work with shear. You got the two blades, they're going in one direction. But torsional shear is when it's being twisted, then there's a shear stress and it wants to snap or pull apart. So these represent shear walls. That's a shear column. You see that in a lot of structures where your elevators are here. If this all framing was framed up in wood, like in some apartment complexes, your stairwells would be out of concrete and engineered so that they reduce shear. So this would be like what? The pole going up through the pagoda. Okay. And these end walls are shear end walls, and they all will resist torsional effects. They'll resist just longitudinal, horizontal, and they will resist this thing trying to rotate around and twist apart. Here's intermittent shear walls. You got some long ones down the long axis of the building, and you've got some short end ones, and still we have this center column. A lot of your super high-rise buildings will always have a center core. That's what this box represents. Down through here would be a center concrete, reinforced concrete core. Mid-rise might be engineered concrete masonry units that have rebar and concrete poured in them. This does the same thing. This is not as structurally sound as that, because you've got basically two pieces of concrete angle iron right here, right? But with proper analysis. Now, the dynamic analysis means the building is moving. Where does it go? And that's what your seismic analysis does. You have to go into dynamic analysis. How much can I vibrate this building? How much can it shake without it falling apart? What are the stresses during shaking? And how is it going to shake? Is it going to shake this way, back and forth? Is it going to go up and down? Or is it going to be a combination of both? And so what kind of frequency, there's that snake dancey thing again, is that building going to want to do? Because the building's got to survive this going up, and it's got to survive this coming back down. And if it can survive those frequencies going up and down, then you got a good chance your building is not going to go anywhere. Now you see this cross bracing in here, in this view. What is that? Okay, well that looks like K bracing, or it represents shear walls going all the way up the side of that building. Or it could mean what? It could mean those are blockouts. Depends on the drawing. The architect and you're going to have to get together. That tells me that that's not an opening for windows. But that's just from my old days of being a structural engineer. Now let's go back up here. What about this one? This can take load that way, and it can take load this way, right? Because you've got this long shear wall. And then you've got this big concrete box that runs up through the building. And if the wind's coming from that direction, or this direction, or the seismic loading is coming from that direction. So how do you think this whole thing? Now, to me, this has a weak point. The weak point is what's tying these two together. If it's light structural steel framing, then you're going to have some kind of bridging in between here so they'll act in consort. If not, you run the risk of differential loading on each side of this frame. So, but with proper engineering and proper design, that's not going to be a problem. Because I bet you, if you looked at the entire structural plans for that, somewhere in between the starting of the second floor and all the way up, depending on how tall this is, you're going to find some major structural elements that tie these two together, major structural elements, so that they will act in consort. Just trust me, the structural stuff's all tied into this too over here and here. Okay, all right. Here we have another concept. So we'd have, maybe you'd use one of these for all your plumbing and these two for elevators, who knows? Or maybe this has got a high occupancy building and you've got 4 elevators in here, and you'd use the elevator core as your 4 big shear columns. And of course you got to tie the rest of the frame to them so that it all acts in one. Again, your mileage is going to vary, and your creativity. As long as you understand the balance of forces, you'd be surprised what you can do. I don't know how much time have I chewed up. Oh, almost 30 minutes. Wow. Time flies. All right. High-rise structures. High-rise structures. Almost to the end of this chapter. We may have to make 4 of these because I want to get into shells and domes and then the joints of connections in the back. So we'll probably have 4 videos. That's fine. High-rise structures. Tall buildings are particularly suspect to the effects of lateral forces. We talked about that before. The taller you get, it's like a column, right? If it's a real short building, it's going to be more rigid. If it's a real tall thing, it's going to be more susceptible to flex, correct? All right, that just makes sense. All right. Tall buildings are particularly susceptible to the effects of lateral forces. A rigid frame is least efficient way to achieve lateral stability and is appropriate only for low to medium rise structures. Now, why is that? Because of the expense of making a 60-story building one giant rigid frame. The Twin Towers in New York were a bundled tube concept. I have a video of how that was built and designed. Part of it was rigid, and the rest of it was meant to flex and twist and turn because it was so bloody tall. So a traditional rigid frame is not as efficient simply because of the expense. The appropriate only for low to medium rise, and I agree with that from my experience as an engineer. As the height of a building increases, it becomes necessary to supplement a rigid frame with additional bracing mechanisms. You can start out rigid, or you can have a partial rigid frame, but then in between these, you need some other kind of framing. Diaphragms, the floors, because we all have a floor in a building, right? So if you had a pan floor and it was reinforced concrete, you could use that as a diaphragm. And they're called diaphragm floors, and they work as a giant shear panel. So if you have a square building and each one of these major floors was a diaphragm, what have you essentially done? You've stiffened your building up, right? Basically, you have a box hooked to a box, hooked to a box, hooked to a box, hooked to a box, with your roof as a diaphragm. So now your tube, even though in between each one of these, we'll call that a floor. This could be a floor, and that could be a floor. This could just be a major floor, a diaphragm floor. Now you've got a tube, like a steel square column, with glass in it and people in it and all kinds of stuff in it. Again, let your imagination not be stumped by the. Look at this one. What do they say about this? A brace tube, okay? A truss tube. They made trusses. Look, see, trusses. So these really represent truss things, and they can be a part of your architectural element. All right. This is a brace tube. The corners are braced. What's that like? Is that like this? My goodness, look at that. Okay. So this is a brace tube. What is this? A perforated shell tube. These are expensive. Oh my God. Yeah, because the outer skin has to be structural. And a frame tube is closely spaced, which was like the World Trade Centers. They called them bundled tube concepts back then. The columns that went all the way up were rigid, and they were really close together. And so they worked like a stack of straws. And it worked real well, unless you fly planes into them. But that's why it collapsed the way it did. Anyway, I have a video on how the World Trade Center was constructed back then. they had foundation problems because it was right there by the water, so they had to use a lot of well points. Remember the straws you have to stick down in the water table to suck all that down. Um, so I will find it from 2019, and I'll add it to the video list, and y'all can watch it, and I'll let y'all know when I put it in D2L. It's a pretty cool video. I mean, it shows it's old, but I mean the World Trade Centers were old. I mean they were so, but it's neat construction. I mean they had to go through a lot to build those things. Let's see. I think we've talked. Okay, that's a frame tube or bundle tube concept. What do they call this? That's the lattice truss. That would be extremely expensive to build. Let's see. And we've already talked about a tube in a tube. Let's go here. This would be a tube in a tube, essentially, if you lattice truss some of this and your structural stuff all tied to it. So you've got a center core, and essentially, now it doesn't float apart like a gust did, but that's really what you're trying to do. Because I guarantee you, every one of these is going to have a central, excuse me, elevator core that runs all the way down through here, where your MEP, your mechanical, electrical, and plumbing, and your elevators go, and that will be a heavy reinforced concrete tube, and it will be used as your center column shear tube. Let's see, and then your stairwells. Where are you going to put your stairwells? You're going to put them fire exit stairs. You can't use the elevator. Where are they going to go? They're going to go around here, or are you going to get them outside the building as much as possible? And if that's the case, then those need to be reinforced concrete, right? Those can be reinforced concrete. And so you got another concrete tube going all the way up with the doors and the stairs so you can exit. All right. So let your imagination run wild with this stuff. As long as you understand the basic concept of how the forces go. You don't have to be a structural engineer. You've already an idea where the stuff's going. Just say, okay, I'm going to push on my building. I'm the big bad wolf. I'm going to huff and I'm going to puff and I'm going to blow my little house down. How do I want it not to blow down? Oh, this is cool. Dampening mechanisms. Okay. We already talked about these things vibrating, right? Especially with the wind. The wind makes these things vibrate. I've been in some super, super tall structures, and they'll sway back and forth. They will sway back and forth like you're on a ship. So dampening mechanisms are viscoelastic devices. Oh my goodness. Viscoelastic devices that are typically installed at structural joints to absorb the energy generated by wind or earthquake forces, progressively diminish or eliminate vibratory or oscillatory motions, and prevent destructive resonances. That's the vibration frequency from occurring. And it happens in earthquakes, and it happens in real tall buildings if you get gusty wind. It's blowing and blowing and blowing. It lets up and blows again, and it gets this thing bouncing back and forth. And that's the dynamic analysis that all structural engineers have to do for super tall buildings. And they have to do it for seismic analysis if they're in a seismic zone and they have seismic codes that they got to worry about. All right, so tune mass damper is a heavy mass mounted on rollers and attached to the upper portion of a tall building with spring dampening mechanisms, having an inertial tendency to remain at rest and thus counteracting and dissipating any building movements. It's basically a counterbalance up here that's got springs attached to it and rollers, and it gets to bounce back and forth. And so if this thing starts to sway over here, what's the reactive force going to do? It's going to roll out from underneath the building movement. The springs will pull it back. Springs will pull this, and blah, blah, blah. It goes back and forth and tries to slow it down. Okay. There's also base isolation. Now this gets really freaky. Refers to isolating the base of a building from the ground with dampening mechanisms to allow the superstructure to float as a rigid body and alter the natural period of vibration of the structure so that it's different from that of the ground, thus preventing destructive resonances from occurring. So theoretically, what happens, and they use some of these kind of foundations, if I'm not mistaken, on the World Trade Center because they were so tall and the foundations were so deep to go to that bedrock, they isolate. You're isolating. Now, these things are huge elastomeric pads. We use them on bridges. They're huge elastomeric pads. The bridge beam would set on that, and the load would go across the top. You'd have a peg going through there, a pin, and then this is pinned into the support mechanism. And it allows this to move, and any vibration from the road flexing is dampened up by the elastomeric pad, and it allows it to move up and down. Now, for a foundation, it's very similar. Some of these have giant springs, some of them are on floaters. There's all kinds of, you can Google this and probably get a PhD lesson in the various kinds of these isolation footings. And what it does is allows the building to vibrate and not be held rigid by the ground. So, but it allows the ground and the foundation to support the building. This gets really freaky design. This is high engineering, high structural engineering through dynamic analysis. Because you have a balance. You have a balance between how much of this squishing back and forth goes on. That's a really scientific term, isn't it? Squishing. And how much resonance you want to dampen. How much of that vibration do you want to dampen? All right. Where are we at here? Oh, come on. We're at 42 minutes. Arches and vaults, and then domes. Let's go arches and vaults, and then we'll go into domes. Okay. Everybody's seen an arch. Okay. There's arches in the medieval architecture of the cathedrals, and there are arches in modern structures. Concrete shells are an arch. Quonset huts are typically an arched. They're a barrel vault made out of corrugated metal and rigid frames. Okay. So what does an arch do for us? We know that columns, beams, and slabs in bearing walls are the most common structural elements. Because why? We're kind of in a rectilinear world, right? Okay, we are. All right. There are, however, other means of spanning and enclosing a space. The Quonset hut was developed during World War II as a cheap way to cover a lot of area with materials that you could ship or carry in a cargo plane and put together a structure. And you can go research Quonset huts if you want. But basically what an arch does is it spreads the load over a curved surface, right? Now, in regular beam construction, sometimes we'll put a positive camber on a beam. You've probably seen some flatbed tractor trailers. When they're not loaded, they look like they got a bow in their belly going to the cab. Here's the truck out here, blah, blah, blah. Well, that's no different than an arch. So when they put the load on the truck, this thing is already bowed up. Then it flattens out. It'll flatten out when you load it down. So it's pre-cambered, which resists the load. If you didn't do that, then you'd have something like this, which would be bad. So that's really what an arch is doing. It's already bent upwards. It's ready to catch the load from above. It's ready to catch the load from above. And, oh, my goodness. And these arches are made out of anything. It can be made out of steel. It can be made out of masonry. The older ones, like if you look at the Roman arches, they're masonry. And they have a key block over here, and they got a key block up here, and this is all masonry. And because if not, you'd have to have a lintel beam to carry the masonry horizontal, like a regular beam. But if you put an arch in, it'll spread the load out over a curved surface. Now, the problem with arches is, what do you do with the end load? If this is going to want to come down this way, this is going to push what? Out that way, right? And that's going to push out that way. And this is going to go down. And this is going to push down. So you got to have a resultant force. Now, the red is the pushing from the load. Up here, the load. And so this reacts against the vertical downward. This is reacting against the horizontal, because this is going to be like a spring wanting to push out, right? And that's your resultant force. That's the combination, the algebraic sum of these two forces going in that direction, okay? Now, they're curved structures for spanning and opening, designed to support a vertical load primarily by axial compression. The transmission of the vertical force of a supported load into an inclined component and transmit them to abutments. That's what we're looking for. What's the name of the end of the arch? It's an abutment. Abutment. It abuts. It's this area in here is the abutment. So depending on the span, depending on the load, these things have to be huge. So like in the Gothic cathedrals, we had those flying arches. You'd have the main cathedral wall, and then you'd have an arch that come down. And then you'd have an arch that would come down. And then you'd have an arch that would come down. And then you would have an arch that would come down. And where the arches ended, had this long, heavy wall, masonry thing, okay? This worked as an abutment. These all worked as an abutment because of flying buttress. The flying buttresses of the cathedrals. Each one of these buttresses acted like the abutment from the load from this arch. And it would carry that over there, and it would carry that over there, and it would carry that over there, until finally it carried it to the ground. Okay? All right. Now we'll get that out of the way so we don't confuse anybody. All right. If I haven't already confused you. All right. Masonry arches are constructed of individual wedge-shaped stone or brick. Well, no kidding. Okay. They're called voussoirs. For more information on masonry arches, see Chapter 5.20. So guess what we're going to see in the future? Yes, indeed. Okay, it takes a lot of talent to make a true masonry arch. Rigid arches consist of curved, rigid structures. Could be timber, steel, or reinforced concrete capable of carrying some bending stresses. There were some barreled wooden arches buildings in off of Washington Avenue years ago that when I was an engineer, I had to go over and do a structural analysis of the old wooden arched basically warehouse, because a guy was buying it and turning it into a restaurant and a bar and a cafe. A restaurant and a bar and a nightclub. You could spend your whole life studying arches. Vaults are arch structures of stone, brick, or reinforced concrete forming a ceiling or roof over a hall or room. These are like the big vaults in Venice or Italy. Usually a vault is it's either a barrel vault like this. It's like half a piece of pipe. Think about cutting a piece of PVC pipe in half and laying it like that. That's a barrel vault. A groin or cross vault or compound vaults formed by perpendicular intersections of two barrel vaults, forming an arch diagonal axis across here. Okay, so if you took two barrel vaults and you mated them together, you would have a groin or a cross vault. Okay, so those are some more definitions. We're not going to get too deep into the structural stuff. I just want you to understand how it works. Okay. So why don't we pick up with domes, and my favorite inventor and engineer, Buckminster Fuller. This would be video 4, because this is video 3. And Buckminster designed the minivan, the 3-wheel drive minivan that got 2 miles an hour and would go so fast and careful. Called the Maxian car. And I said Maxian house. And so now we get back to where we're supposed to be. Yes, this is video 3, structural patterns, and we put on video 4. Right? Okay. All right. See you on video 4.